Okay, good morning, everybody. I'm sorry I can't be there in person, but I'm actually in South Africa, getting ready to board the Joides Resolution just a little bit later this morning to go on a drilling expedition in the South Atlantic. I'm actually recording this from my lovely hotel room right now. But through the miracles of the fascinating modern age in which we live, I am still able to be here to introduce Adam remotely. Adam Woodhouse has been a distinguished postdoctoral fellow here at the Institute for Geophysics since September. And just between us, I think we're really lucky to have him here. Adam got his bachelor's in science in paleontology, first class with honors, from the University of Portsmouth in 2015. His master's is in applied and petroleum micropaleontology with distinction in 2016 from the University of Birmingham, where he worked with Kirsty Edgar and Tom Dunkley-Jones on a project reconstructing the response of tropical planktic foraminifera to the Eocene-Oligocene transition. He got his PhD in micropaleontology from the University of Leeds in 2021, where he worked with Tracy Ayes. His thesis was titled Death in the Oceans, Extinction Risk in the Marine Realm. In 2018, he also participated in IODP Expedition 375 to the Hikurangi Margin, which I think most folks at the Institute for Geophysics are pretty familiar with. I don't know which of these projects or his current postdoctoral work Adam will be talking about today, because I'm recording this on Saturday the 9th. But whatever the topic is, I'm sure it's going to be super interesting, and I'm very jealous that you all get to sit there and listen to it. So without further ado, I'll say, Adam, take it away.
Right, so my primary research concerns are using large microfossil occurrence datasets and the marine micropaleontological record to answer key questions in evolution and extinction, mainly through the Cenozoic, but I'm interested generally in a deep time. And I focus primarily on a single fossil group. And okay, I guess it's going to collect the screen. Okay, I focus on the group which are the planktonic, Cenozoic planktonic foraminifera. So why focus on this group in particular? So they have the best species level fossil record of all fossil organisms like that we are aware of. Their species level record is better than the best genus level record of macrofossils, which are the bivalves. So really good record. They have a really refined taxonomy that we've been working on for, especially in the last couple of decades, but for close to 200 years. And there's a lot of people like constantly revising these and making sure that our taxonomy is correct. And also because they're single-celled organisms about the size of a grain of sand, and they're planktonic, they're highly abundant in the world's oceans and relatively cosmopolitan throughout the world's oceans. So if you drill anywhere or pick up any sediment from the bottom of the ocean, in certain areas such as the middle of the Pacific Ocean where there's no terrigenous input, often up to 90% of the sediment is actually made solely of these skeletons. That's really useful for evolutionary studies, because instead of getting a bone every now and again through the record, if we just drill straight down, we get a continuous record of sedimentation of these forms, so you can actually see evolutionary transition, and you can watch them transition from one species to another through time. And each skeleton stores the entire life history, the ontogeny, and also each one of these the forams make their skeleton from calcium carbonate directly from the ambient seawater, so they actually preserve a biogeochemical fingerprint of the surrounding seawater chemistry. So they're really useful for paleoclimate studies, because they can give us the temperature of the water at the time. So the talk layout today, I'll introduce first the Triton set, which I made during my PhD, and then go through three applications of it. First, looking at the biogeographical, Paleo Ecological, and Phylogenetic Trends of the forams in the record. Then two, look at spatial dynamics within speciation in the forams, whether or not during greenhouse periods, species are evolving further from the equator because it's warmer. And then finally, a really preliminary study looking at bipartite networks using the record. So part one, introducing Triton. So we published this last year in Scientific Data, where I was a co-first author. So quickly introduce Team Triton. So it was the University of Leeds with two of my supervisors, Tracy and Alex. I'm at UCL in London with Jeremy Young, two researchers from Oxford, Isabel, my co-first author, and Dr. Erin Stout, and then two researchers from the museum, Bernatacunda in Berlin, who were both extensive experience in making large microfossil occurrence data sets. So the aims and objectives of Triton was first to assess the completeness of previous micropaleontological records, and then such as Neptune, which is what David and Johan made at Berlin, and then create a new strictly planktonic foraminiferal Cenozoic record to give to the overarching community to do large macroevolution and paleoclimate studies, and also for me to use not only to finish my PhD, but in my postdoc and hopefully future endeavors as well. So a quick background on how we get these microfossil occurrence data sets. So it starts off with ocean drilling, obviously. We've got to drill down into the ocean floor and collect sediment. So ocean drilling really started at the Challenger expeditions in the late 1870s. But the proof of concept of what we could call, that was mainly dredging, but the proof of concept of what we call ocean drilling today started with Project Mohole from the late 1950s to the 1960s, which proved that we could extract sediment from a mobile platform from the ocean and pull sediment up onto up to the surface to study it. And then this has been followed up by the numerous iterations of the ocean drilling programs, which is now at its fourth iteration of the International Ocean Discovery Program, or IODP. So we have a number of different vessels to extract the sediment. First off, we have riserless drilling, which is mainly achieved by the JOIDES Resolution, which is the ship here on the right, which is sailing off of Cape Town here back in, I think it was the early 2010s, and obviously it's just sailed off of Cape Town again with our own Christopher Lowery on board. Another one of the vessels we use is the Chiku, which is slightly larger than the JR or the JOIDES Resolution. And this is actually a riser drilling vessel, which means that there's circulation of drilling mud between the ship and down on the sea floor. This allows for deeper drilling at higher pressures and extraction of deeper sediments, and has been used a lot across the Nankai Trough. And then finally, we have mission-specific platforms where the environments may not be conducive to drilling with the JR or the Chiku. So this can be the ASEX cruisers here pictured on the right, where we have the retrofitted drilling vessel moving around with two icebreakers, which are breaking up the pack ice to stop it from moving the ship around too much and causing any danger. And then jack-up platforms such as that used to drill the Chicxulub crater on Expedition 364, which again, Chris Lowery was a part of. And then finally, the vast majority of sediment is probably actually obtained from the dozens, if not hundreds, of vessels which have which are equipped to take shallow piston cores and box cores, and there's a number of vessels that even UT uses very often. So once we have the sediment up on board of the ship, or we brought it back to land, we can wash it and sieve it, and all kinds of little beasties and bugs come out of it. So on the top left is we have the forams, which is my favorite, obviously. And then we have calcareous nanofossils to the right, another calcareous fossil, obviously by the name. Radiolarians, which are made of silica. Dinoflagellates, which are made of organic walled diatoms, again silica. And then fossil pollen and spores, which are again made of organic material. And all of these records, not all of them, but a lot of these records have been stored subsequently in many different kinds of databases, which are shown here on the right. And this was the basis of Triton, taking all of these databases, standardizing all of the data and putting it all together just for the foram data to create Triton, which is named in honor of the Neptune dataset, as Triton is the son of Neptune in Greek mythology. So now we have all of this data. The next step was to identify everything that was missing from the record. So I searched through all of the drilling proceedings from 1968 onwards and found out all the sites which weren't currently in the database. And the literature mined all of this data, got the most up-to-date taxonomy up to 2021, tried to find the species ecology, which I'll delve into a little later, how we figure that out precisely. And then all of the chronostratigraphic data within the drilling proceedings. This includes biostratigraphic events such as first occurrences and last occurrences, paleomagnetic polarity reversals, and then isotope stratigraphy as well. So we have the best, most up-to-date chronostratigraphy to assess these sites. And the reason why we needed this is we needed tie points to perform to create linear sedimentation models, not totally linear because we use generalized additive models to model sedimentation rates between each of these tie points for every hole. And the fact that we know the modern coordinate of where we picked up the where we drilled the site and then we can go back through time and find out what the date, in millions of years of when that foram was deposited. We can then use plate rotation models to back rotate and find out the paleo coordinate of where that fossil was deposited 60 million years ago or so, or anywhere. So yeah, so now we have species taxonomy, species ecology, the age of deposition, and the position of deposition in time. So how does that look now? On the left, we have the data sets and databases which make up the most of Triton. So a lot of the data is from Pangaea and Neptune, but also from IODP and Forsen's, which is a quarter data set. And on the right, there's a lot of data here, but this is a comparison between Neptune, the previous largest foram database, and Triton. And the most important thing is that Triton actually now has 4.5 times more occurrences than the previous iteration. So that makes it the largest single fossil group occurrence data set ever created so far. And to put this into context, if we compare that to the paleobiology database of macrofossils, if we look at the bivalvia, they have just under 200,000 occurrences, and that's for the entire 540 million years of the Phanerozoic, whereas we have over 500,000 for just the 66 million years of the Cenozoic. So if we look at that spatially, how that compares to Neptune, as you can see, there's a lot more coverage in Triton. A lot of that is from the shallow coring efforts, especially around the Mediterranean and North Atlantic, as a lot of effort has been concentrated around there. So you can clearly make out the outline of most of the continents. If we look at in a spatio-temporal aspect, we can see that Triton, on the left, we have latitudes, and on the bottom, we have age in millions of years. We can see clearly that Triton fills in a lot of the gaps in our record, especially in the deep time mid-latitudes. However, annoyingly, the low latitudes are chronically undersampled and underrepresented in not only Triton, but in pretty much all Cenozoic and Cretaceous fossil databases. This is a number of reasons, including sedimentological reasons, but as well as historic biases in collecting fossils. Yeah, so to summarize, the Cenozoic is the largest sedimentary archive that we can use to look at deep time paleontology. Triton now represents the largest occurrence data set for any one group. And Triton will continue the legacy of previous data sets such as Neptune to help us answer questions on climate and evolution through the past, present, and also into the future. So part 2 is the first application of the Triton record. So this is looking at the biogeography, Paleo Ecology, and Phylogenetic Trends of the forams through the record. So the aims and methods are using Triton is to assess those trends, and by doing this, we took the entirety of Triton, binned it into 88 time bins of equal length of 0.75 million years, and data extracted for each species. So first the paleolatitude, then the species ecology, and then the species phylogeny. And the plots that I'm about to show you are the proportions of occurrences in Triton per one of these 0.75 million year bins. So let's put it into context quickly for those who may not have intimate knowledge of Cenozoic paleoclimate. So here we have the Cenozoic, and moving upwards in green, we have the benthic delta 13C record. We have then in blue, the benthic delta 18O record, magnesium calcium temperature records, and then at the top finally is carbon dioxide records through time. So what we have really going from left to right is a general trend of warming followed by cooling. So we experience in this colored red box here, first as a greenhouse world, and then at the Eocene-Oligocene boundary, we isolate it as a Icehouse world. But it's a bit more complicated than that, but for complexity's sake, I assign it as this from the point when Antarctica established permanent continental scale ice sheets. So moving from left to right, first we get warming up into the first of our major paleoclimatic events in the Cenozoic, which is the PETM here, where we get temperature increases of up to 8 to 10 degrees in the space of 100,000 years globally. We have sustained period of warmth called the early Eocene climatic optimum, or the ECO, which I'll refer to throughout the talk. And then after the ECO, we have from 50 million years onwards, we have a period of time moving forward, which we term the descent into the Icehouse. So there's a general cooling trend moving downwards through time with a few hiccups of warming. So the first hiccup is the MECO here around 40 million years ago. And then it's here, the EOB, where we get that major cooling event, major global cooling, and thermal isolation of the Antarctic mainland. So we have establishment of continental scale ice sheets. We move through the Oligocene, which pretty much stays relatively stable. The Oligocene-Miocene boundary, which is a warming and cooling event. Then we have a final warming hiccup during the Miocene climatic optimum from 17 to 15 million years ago. This was caused by the Columbia River basalt, which is the last large igneous province of large magnitude within the geological record, or the youngest anyway. And then finally, our last final major event is the intensification of northern hemisphere glaciation, which is the point where we develop into a bipolar cryosphere world, and we get our ice sheet on Greenland as well. So now we have a northern and southern hemisphere ice sheet. So now we have an idea of what's going on generally through the Cenozoic. Let's look at our biogeographic trends first. So on the left here, we have our modern, so I'm going to look at the provinces of planktonic foraminifera, the faunal provinces. So on the left here, we have the approximated boundaries of our modern day provinces. So you can see that they're generally relatively latitudinally continuous, but for the sake of keeping it simple, I've used the straight lines of the current climatic provinces of the polar, temperate, subtropical, and tropical provinces. And as I showed before, that climate has changed a lot during the Cenozoic. So there is actually reason to change these going through time, as our latitudinal temperature gradients have steepened as we've moved more towards an icehouse world. However, again, for complexity's sake, I'm going to keep it as they are, but potentially I'd like to make them more dynamic in the future. So what trends do we get when we look at our provinces? Again, blue is polar, green is temperate, orange subtropical, red is tropical. So there's a major pattern. You can pretty much see straight away that the greenhouse record here, Paleocene and Miocene, is dominated by temperate occurrences, whereas the Icehouse record is dominated by tropical occurrences. And then noticeably, we also have a blip up here of increased polar records in the last 3 million years or so. And this is probably mainly due to the fact that those shallow sediment cores I mentioned before, there's been a lot of concentration around Greenland and in the North Atlantic. So what could be the reason for this huge shift across the greenhouse icehouse transition? So potentially we might have a biological origin. I mentioned that the tropics might become thermally prohibitive to life during a greenhouse world. So potentially what we're having here is a shift of species. As the Earth cools, do we get a shift of species from the temperature region into the tropics, where it's become more habitable now that the temperatures have cooled down a little bit? So is this migration from the high to the low latitudes, and tracking those temperature gradients through time? But also there's I showed before that the Triton record is chronically undersampled in the tropics, unfortunately. So there's potentially sedimentological and sampling reasons why this might occur. And what I mean by that is mainly the fact that the calcium carbonate compensation depth, which is the depth in the ocean where calcium carbonate will dissolve out of the water column because of temperature and pressure. During the greenhouse world, this was 2 kilometers higher than it is today. It's about 4 kilometers depth average in the modern ocean. It was about 2 kilometers depth in the greenhouse ocean. So the problem with that is that you only get carbonates, which are highlighted here in blue, preserved on paleoceanographic highs, such as mid-ocean ridges, and on plateaus, such as Walvis Ridge and Shatsky Rise, etc., which is one of the reasons why a lot of drilling projects have actually been focused on targeting these rises, because they've been above the CCD consistently since the Cenozoic, since the Cretaceous period. That also causes an issue because there aren't actually too many of these rises which have been consistently over low latitude. So that causes an issue to capture some of this low latitude well-preserved record. Yeah, as I mentioned, the low latitudes here in Triton are lacking. So another one of the reasons is that around the margins of the Atlantic especially, but also in the Pacific, we have, during the Paleocene and the Eocene, there are really extensive deposits of indurated cherts and porcellanites, which when you drill through them, they tend to fracture and break and wash away the softer carbonate. So a lot of the time, the some of these Paleocene, Eocene records that we're really interested in to assess how greenhouse worlds work are completely lost. Right, so now we're getting on to the Paleo Ecology. So I'll just give a quick primer on how we assess Paleo Ecology in planktonic foraminifera and what it can tell us about ecology of the species and through time. So the water column has a distinct ratio in delta 13C and delta 18O going down. So as we move up through the water column, we get a higher enrichment of delta 13C, and this is because in the photic zone, photosymbiotic algae are preferentially uptaking carbon-12 during photosynthesis, which enriches the surface waters in carbon-13. On the plot on the right here, I've also highlighted that in planktonic foraminifera, increased symbiotic activity and increasing delta 13C. This is illustrated here in this painting by Richard Bisley. These tiny little yellow dots around the forams, these are actually dinoflagellate photosymbiotic algae. So actually the forams have a microcosm around their tests. So not only do they often live up in the water column, but they'll be super enriched. Their shell chemistry will be super enriched in carbon-13 because they're also photosynthesizing even more. And then going down through the water column in our delta 18O record, we have an increasing oxygen 18 moving through the water column, which is caused by the temperature-dependent fractionation of oxygen with temperature. And all of this together gives us a biogeochemical fingerprint, which if we look at modern species where they live, we can see that they obey this kind of law of this increase in delta 18O and increase in delta 13C, depending on where they are in the water column. And more importantly, we can look at fossil specimens and determine their ecology and where they were living in the water column at the time. So yeah, we can lump these delta 18O and delta 13C records into specific groups. So here's a plot I made of a study I did during my PhD. So moving up, we're going from subthermocline species, thermocline, the surface mixed layers forms. And as we're moving to the right, we're getting more enrichment of symbiotic algae. So yeah, that's how we can then assign them to these distinct groups. So we have two groups which are in the surface mixed layer. One is asymbiotic and one is symbiotic, shown here by that enrichment. And to these four ecogroups, you can also add high productivity and upwelling forms, and also species which tend to persist within high latitudes, which is primarily within the modern day in our bipolar world. So we have these 6 ecogroups now. So let's look at the patterns that they exhibit. So again, we have here, so red is our symbiotic, orange is our asymbiotic. So the red and orange are our surface dwellers, cyan is thermocline, blue is subthermocline, these are our deeper dwellers, yellow high latitude, and green is upwelling. So we have, again, we have this huge transition going over the greenhouse icehouse transition, a turnover in our groups where we have dominance mainly of our shallow dwellers in the early record and our deeper dwellers in the icehouse record. So if we just go through this record, first off, we have symbiosis that re-evolved, which is the red one, because at the KPG mass extinction, all of the symbiotic planktonic foraminifera were totally exterminated. So it took them a few million years to re-evolve the ability to form symbiosis with photosynthesizers. And then there in the early Eocene, around in the eco here, around 50 million years ago, this is when symbiotic forms have not total dominance, but the highest level of dominance. But interestingly, as we move from around 50 and then downwards through 40, we have this kind of first step shift where we have a drop in our surface dwellers, which is taken up, accommodated by an increase primarily within our colder dwellers, including our high latitude forms. But then we have another step where we go from relatively even proportions to one where the warm water species have the lowest portion through pretty much the entirety of the record. And these, for some reason, these tend to occur at 50, which is at the initiation of the descent into the icehouse. And then after the Middle Eocene climatic optimum, here we get the second drop, where the lowest abundances are seen straight after the Eocene-Oligocene boundary. So the EOB is actually the biggest extinction event in the planktonic foraminifera since the KPG, and it seems to have mainly been amongst the species which live in the upper water column. So it seems that the intensification of the Antarctic ice sheet reorganized ocean circulation, and also the water column, which caused extinction of these forms. And then also notably, we have a huge increase in our proportions of high latitude forms moving towards the modern, around the same time that we have our northern hemisphere ice sheet starting to form. So this is likely to do with that, but also, as I mentioned before, there's been a lot more high latitude sampling, so there's probably a slight sampling bias in not only this part of the record, but some of the record, which needs to be addressed. So finally, our phylogenetic trends. And what I mean by this is that there are two-ish distinct wall types of planktonic foraminifera based on their porosity. And these are the macroperforate with pores over 2 microns here, usually macropores, and the micro/medioperforate with pores below 2 microns, which are hard to see in this image, but you can see them inside of this test here. And what that means, why that's important, is that the macroperforate species, all of them in the Cenozoic descended from 2 species which crossed the KPG extinction event. So we know this is a monophyletic clade, so we know the entirety of this. These macroperforate forms are all descended from these 2 ancestor species. However, the microperforate, these is actually a polyphyletic clade. This means that they've evolved multiple times through the Cenozoic due to convergent evolution, usually from benthic ancestors, and this occasionally. So this is actually multiple different with multiple different genetic backgrounds, pretty much. So if we look at those patterns of these phylogenetic patterns through time, what we see is early on we have this dominance of microperforate taxa, which is the only time in the record where they're dominant, over 60% or around 60% of all occurrences are microperforate, and this quickly drops to very low. We get an increase again across the greenhouse icehouse transition, and then a further increase as the second ice sheet starts to form in the northern hemisphere. So what I think this means is, in the early days after the devastation of the Cretaceous Paleogene impact, as we have with in the early stages after all major extinction events, our strategists and opportunistic species tend to dominate the faunas. So microperforates tend to be our strategists, so I assume that's what we're seeing here. It takes about 5 or 6 million years for them to become outcompeted by the macroperforates, because it took the macroperforates a little while to re-evolve and get back to where they were prior to the mass extinction. Well, they never got back to the same level of diversity they were in the Maastrichtian, but it took them about 6 million years or so to get back to a good solid standing stock. Then across both the Antarctic glaciation and the Northern Hemisphere glaciation, we see these increases in the abundances. And that's mainly likely due to the fact that when we have these increases, we get upwelling across continental margins due to the formation of cold waters around Antarctica and in the Northern Hemisphere, causes upwelling around continental margins, eutrophication of the water. Opportunists like that kind of environment. So to summarize biogeography, we have this turnover across the greenhouse icehouse transition, its potential biological and sedimentological and sampling explanations. Paleo ecology, again, we have the turnover between shallow and deep dwellers across the greenhouse icehouse, and this conforms with generally what we see when we do paleoclimate reconstruction of the Cenozoic. That from a warming to a cooling environment, this is the kind of pattern we would expect within certain ecogroups. And then finally, our phylogeny, our strategists become more dominant when we have these big ocean structure changes such as KPG and the EOB, and also during the Northern Hemisphere glaciation. So the second application of Triton is looking at the speciation patterns and whether or not species are evolving further away from the equator when times are hot, such as in the greenhouse. So yeah, looking at the locales of speciation, have they changed through time, and whether or not climate is playing a general role, and also what maybe this indicates for the future if climate is playing a role. So, quick background on what this means, because this relates to latitudinal biodiversity gradients, where in the modern day, the latitudinal biodiversity gradient is situated around the tropics, and diversity tends to decrease going towards the poles. This is a simplified plot from Phil Mannion et al. So along the bottom, we have Phanerozoic time, the red line is relative temperature. And the blue boxes are periods when we have extensive glaciation of the Earth. And all of these points here are studies which have pinpointed the point in time where we have our highest diversity. So along the side here, 0 to 60, these are latitudes. So the higher up, the further away from the equator, we have our maximum biodiversity, which seems to indicate that during a greenhouse world, it seems to be further away from the equator, which is kind of what we would expect, isn't it? So I supplement these with a couple of studies performed by my colleague Bethany Allen at the University of Leeds, who looked at the Permo-Triassic and showed that diversity was highest at 60 degrees during that Permo-Triassic mass extinction when things got very, very hot. Emma Dunn from the late Triassic in Birmingham, and also a study by Raja and Keesling, which actually did look at microfossils through the Cenozoic and actually showed that during the greenhouse world, we do have these mid-latitude peaks, and these peaks move towards the equator through time. So it kind of backs up the fact that we might expect species to speciate further from the equator. However, Jones et al. Said that there are major issues with LGB construction, especially between 220 million years ago, which is this period here, which is the period which is the greenhouse, the period that we're interested in, and finding out whether or not potential future climates may be firmly prohibitive to speciation and biodiversity at the equator. So there's been multiple studies on the PETM, that time interval I mentioned when it got about 10 degrees centigrade higher globally, well, in high latitudes anyway, about 6 degrees globally, it increased by in 100 kiloyears. So multiple studies have actually shown that species, tropical species, moved away from the equator during this single event. But I'm more interested in whether or not greenhouse environments, the entirety of the greenhouse environment, is firmly prohibited, not just a single event, which is more, so the greenhouse as a whole is firmly prohibitive, not just that single PETM event. So I mentioned that study by Raja and Keesling, which they showed mid-latitudinal peaks during the greenhouse world in planktonic foraminifera, but also radiolarians, diatoms, and calcareous nanofossils. So here we have their study, which showed during the greenhouse world peaks in the mid latitudes, and then Icehouse world peak towards the low latitudes, which is great. However, they used the Neptune dataset, which, as I mentioned before several times, the Triton dataset is lacking in the low latitudes. So unfortunately, the conclusions that they have that the mid latitudes were the peaks of high biodiversity during the greenhouse world, if we just compare to the record, I believe all of this is actually being driven by sampling. I think they're right, but I don't think their conclusions are correct with using that data set. So the methodology that I've used is using Triton, assigning each of the 380 or so planktonic foraminifera their speciation and extinction timings, which we've got from biostratigraphy. So we know when species become extinct, near to the nearest 100,000 years or so. So any occurrences after our extinction points, we can trim away, because this is probably due to reworking or misidentification, and any occurrences before we know that a species appears, it's likely due to misidentification, because when one species evolves into another, it's not a single point in time, this is one species, this is the other. There's a very gradual change most of the time. So it can be difficult to identify what is actually a specific species. So taking all this data, once again binned into 88 time bins of equal length, and then the earliest occurrence in Triton was extracted, and the paleolatitude of that occurrence was extracted. So using generalized least squares regression and modeling the variable, the paleolatitude of speciation, we're using explanatory variables of climate. So this includes the benthic temperature, as I showed before on that graph, magnesium, calcium, delta 18O, delta 13C, carbon dioxide, from all of these references here. Also assigning species to the Icehouse or the greenhouse regime, depending on when they speciated. Also the eco groups were assigned, and also the percentage of samples located between 23.5 degrees north and south. So we can see whether or not the sampling universe is driving these patterns, or whether or not it's actually climate. So results. So first off, I'll walk you through the graph on the right. So upwards, we have time moving forwards this way. And then moving from left to right, we have the samples. So here it shows pretty much the same as our provincial record, which showed that increase in tropical samples as you move across the EO boundary here, highlighted in blue. And then this portion here, these are our paleolatitudes of speciation. And the red highlighted bar here is the tropics. We have our green, our delta 13C, our delta 18O, our magnesium, calcium, and our CO2. So if you just take a quick look, we can actually see that during the early Cenozoic, there does seem to be a sparsity of first occurrences occurring within the tropics. But again, how much of this is driven by sampling? So modeling the paleolatitudes of speciation. The best performing model had delta 13C, temperature, and the percentage of tropical samples as statistically significant. So great, it brings out temperature, saying it's a positive relationship. So it's saying that when temperature is higher, species first appear further away from the equator. Cool. And it consistently does this. Additionally, it had a negative relationship with delta 13C, and this is likely due to the fact that during the greenhouse world, we have these negative excursions in delta 13C associated with the ECO and the PETM. These are injections of isotopically light carbon, primarily from the North Atlantic igneous province during the early greenhouse world. So we have temperature and a temperature, delta 13C, which is pushing temperature as well, associated with our paleolatitudes of speciation. But of course, tropical sampling was also statistically significant, so we can't rule out, we can't say whether or not it's just sampling or it's just tropics, or it's a little bit of both. So what is really going on? So the pros of this research and other research is that we have evidence of multiple studies show evacuation of the tropics during the PETM, and there's evidence of temperatures up to 40 degrees centigrade during this period in time, which is an important temperature because this is beyond the temperature where most organisms are able to metabolically operate efficiently. Here we showed a model support for temperature associated with latitude of speciation. And then a study by my colleague, Isabel Fenton, has shown that latitudinal biodiversity gradients of the forams using Triton are associated with temperature in the later part of the Cenozoic. Our cons, I mentioned before, we have those Paleocene Eocene cherts hindering sediment recovery, a higher CCD of 2 kilometers during the greenhouse world, and then low latitudes historically undersampled, and of course we have that statistical significance of the tropics, of tropical sampling. So I'm trying to resolve this, how we can better resolve it is, number one, to perform a vast literature mine of the onshore records. So there's much of the Tethyan realm, and when India was situated on the equator, there's not much data from India in Triton. So I'm looking to put in a proposal to hopefully rectify this record and find out whether or not we can truly separate sampling from temperature. It also perform some subsampling approaches, and then eagerly await the results of expeditions 387 and 388 if they are no longer postponed, which are on the equatorial margin of South America. So to summarize that section, the paleolatitudes of speciation appear to be changing with climate development through time, and this is likely driven by both abiotic, as in climate, and sampling effects, but how much of this biological signal is actually attributable to sampling. And if we can really work this out, this may provide increased support to current observations such as those by Lucas Yonkers et al., who looked at the distributions of planktonic foraminifera prior to the Industrial Revolution and today, and has shown that species are already moving away from the equator and migrating to more higher latitudes, which is worrying. So part 4 is using our bipartite networks. This is a very preliminary study. This is a co-study with Dr. Anshuman Swain at the University of Maryland, who is a statistical whiz and is really good with these kind of things. And I'm learning a lot from him, which is really great. So, bipartite networks. This was the question that I asked him the first time. What is a bipartite network? So a good definition is a specific class of complex networks that have nodes divided into 2 sets, X and Y, whose nodal links occur between the 2 sets and not within a set. Basically, they're really good for assessing community interactions. So Anshuman performed a study using the leaf record of leaf record through time and the traces of insect behavior on those leaves. So using one, so X would be the leaf species and Y would be the type of trace on that species of leaf, and then seeing what the interactions were moving through time and whether or not those change through time. So in our case, instead of using leaves and insect traces, we're using paleolatitude versus ecology or morphology. So I'll quickly delve into morphology in a second. So the aims and methods of this, again, using Triton, applying bipartite networks. And the methods for this is binning all of our paleolatitudinal data into degrees of 5 degrees of latitude, and then using 2 resolutions, one of them 1 million year time bin resolution for the last 66 million years, and also 100 kiloyear resolution for the last 15 million years, to see whether or not our shallower record allows us the ability to look at a higher fidelity to look at the planktonic foraminiferal record and the community interactions. So there's lots of different measures we can use with bipartite networks, but the one that I'll be highlighting in this really quick preliminary talk is species specificity, which I shall explain now. So here we have one of our network plot. So we have Cenozoic time along the bottom again, and this is our species specificity. So high is light colors, low is dark colors. So this is the eco group. So basically what high means is that in that 5 degree latitudinal bin, in our 5 degree by 1 million year latitudinal bin, the lighter the color, the less eco groups are present within that bin. And the lower, the darker the color, the more eco groups are consistently present within that bin. So that means they're all having a good time if it's really dark, and they're all either specialized or not having a great time when it's really light. So the primary patterns we see here during the Eocene climatic optimum, when it's really hot, we get a lot of high specialization, which is really interesting. And I'm trying my best to work out what is going on here, because it doesn't occur in the high latitude, southern high latitudes, but it does occur in the mid latitudes. So maybe high latitudes have the highest diversity because that's where it's not firmly prohibited. So maybe that backs up further the hypothesis of the previous talk. Also, we have in the high latitudes in the modern, we have specialization, which, as I mentioned before, the current latitudinal biodiversity range peaks in the middle and peters out towards the high latitudes. So it's kind of like, it's intrinsic that the high latitudes are going to have a low number of eco groups and species as well. And what's really interesting, I'll flick through this a few times, is that as we move towards, for the last 10 million years or so, we see these bands of low specialization, generalization, moving towards the equator, which is really odd. So I'll jump into that with the 100 kiloyear resolution in a second after I go through morpho groups. So morpho groups, I won't go into too much detail. There's 17 of them rather than 6, so it's a bit more complicated. But it's, you know, it's basic changes in morphology. So is it a conical shaped foram or is it a round globular shaped foram? But there's different classifications we use. So the primary patterns we see here is during the post-KPG extinction. Again, a lot of morphological specialization. And this is because basically there was only one morphotype which survived the Cretaceous Paleogene extinction. So it took a long time to build up morphological complexity, which is a study that Chris actually did following in recent years. And it showed it takes about 10 million years for a morphospace to become reoccupied back to pre-extinction levels. And then we have this period after the Eocene Oligocene boundary where you can see it's kind of white banding, high specialization. And it's not high specialization because, again, we have this extinction across the Eocene Oligocene boundary, and the only species which tend to survive they all look the same. And that's what's led biogeographers to term the Oligocene the Uglyocene, because it's really difficult to find out where you are in time because there's only about three genera, and all of the species tend to be incredibly familiar. So this Uglyocene actually shows up within our record, which is really cool actually. Again, we have high specialization within the high latitudes, as you'd expect. And then those bands do kind of show up, but not as prominent as they were on the eco group record. So finally, we'll look at those eco groups at a higher resolution. So looking at the last 15 million years at 100 kilyear resolution. So the data is a little bit choppy from basically anything prior to 6 million years ago. There's not much we can really gain from that. And this is just because of the nature of records. When you drill down, the first thing you hit is the Holocene, and you've got to drill deeper, spend more money to get back to the Miocene and deeper. But that record still is, those zones of low specialization still seem to be more or less present, but this may just be my eye, and I've been staring at it for too long, which we were all aware of, and it happens when we are staring at charts and graphs and seismic data, etc. But I see that this kind of step pattern rather than just gradual decline moving over here. So it seems to be like a funneling. And what I think is going on here, this is across the, when we develop our Greenland ice sheet, this is the intensification. So we're getting this shift of a generalized zone from higher latitude or mid latitude down to the lower latitude, and then it kind of stabilizes again once we've formed that ice sheet fully, which I think may be basically like global community dynamics. As the globe is cooling and we get intensification of our meridional temperature gradients, we're actually getting species migrating further towards the equator, towards establishing the modern biodiversity patterns we've seen. So I wonder if before that, if we compared to our modern patterns in forams, we'll get a completely different pattern during that early Pliocene. So yeah, to summarize that part, the final part of the talk, eco groups highly specialized during the eco and in high latitudes, and we have these low specialization zones moving towards the equator in the latest Cenozoic, maybe new niche exploitation due to intensifying cryosphere development. Morpho groups highly specialized following the post-ATG, as you'd expect, that everything dies, and then the Eocene following the Eocene boundary, and again in high latitudes, and it shows minor evidence of those zones of low specialization. So to conclude, Triton, the largest microfossil occurrence data set ever created so far. Great for applications for global macroevolutionary and paleoclimate processes. Our trends in biogeography, Paleo Ecology, and Phylogeny tend to show a turnover between the greenhouse and Icehouse regime, but a lot of this these patterns may be driven by sampling and sedimentological problems. Speciation appears to be driven partially by climate. However, again, there's sampling issues which I'd like to resolve. And our networks, we see that major patterns are recorded that we would expect from the record, but also we have that reorganization of communities across latitudes as we approach the modern. So too many people to acknowledge individually, but all these people I'd like to thank, and funders, etc., for this work, and all of you for coming and listening to me blabber on about forums. Thank you.
Thank you, Adam. We'll start with questions from the room, if anyone has any. Okay.
We're probably in the middle of one of the biggest revolutions in ocean chemistry that's ever happened, short of maybe the meteorite impact. There are other drivers now in water chemistry, like acidification. And it's too early probably to say, but what's your take on how speciation is gonna react to drivers like that? We're seeing latitudinal shifts, and that's temperature, and maybe CO2, I don't know, but acidification is the one that I hear from people now, is that in terms of the microbiota is the big threat.
Like pteropods and stuff like that.
Yeah. So how do you see that?
The CCD and the lysocline is shallower at higher latitudes in the modern day as well. So we'll probably see similar shifts actually, where we're seeing stuff moving. Well, actually, that's the issue, because acidification will move things towards the equator, but heat will move things away from the equator. So we might get, again, the reestablishment of bimodal and latitudinal diversity gradients in the marine realm, where especially our calcitic organisms can only occupy in the mid latitudes, which is obviously, these species have spent some of these species have lived for 20 million years. These are species which are preconditioned to specific environments, and no species have preconditioned to a rapid change on the scale of the ETM. So how much can the record really inform us when nothing like this has ever really happened? Another one of the big issues is when the PETM occurred, there weren't any ice sheets. So you didn't melt any ice. And the problem when you melt a lot of ice is you change ocean structure. And the biggest extinction event for the plankton foraminifera is the Eocene-Miocene boundary, which is a cold event. And it wasn't the cold that killed them. It was the reorganization of ocean structure, which is, changing salinity and everything like that. So if we melt the ice sheets, well, if the ice sheets do melt, they don't tend to, actually they tend to diversify when it gets hot, but they tend to die when the ocean currents.
The CO2 uptake now, we've got 40% of the CO2 in the atmosphere. 40% of the CO2 we're putting out now is being absorbed in the ocean, and we're talking actively now about bioengineering. So we're let's make the oceans take up more CO2, but I don't think people think about the ecology of the oceans when they talk about that.
Yeah. One of the great things about forums is they have a great record, but we don't actually know. We count them as like a base of the food chain because they're zooplankton, they're microscopic, but we don't actually know what eats them. So we kind of use them as we can't really say that, if the forams die, it's going to cause a cascade effect across trophic levels. But obviously there are organisms which are calcitic, which food chains do depend on. So if we increase that CO2 and obviously the uptake is going to be things dissolved, there is going to be something's going to cascade, but obviously the ocean is just so annoyingly complex that it's hard to know, it's hard to predict what's going to happen.
Any other questions from the room? And if anyone's got any questions online, could you raise your hand? Oh, Marcy. Yeah, could you unmute yourself?
Hi, Adam. My name is Marcy. I just want to say thanks for creating this tool. This is really great. I work with nanos mostly, and mostly in the Gulf of Mexico. And forgive me if you said this in the beginning, but how much of your data went into your database from the Gulf of Mexico? Because I'm just thinking there's only one, maybe two DSDPs that occurred in the Gulf of Mexico. So a lot of the data comes from industry drilling. And I just wonder what kind of basin specific patterns we might be missing because of that.
Yeah, I actually one of the charts I missed out in it was going to come before the provinces, but I didn't have time. Was actually I separated all of the oceans into separate basins, and you can see how our sampling in different oceans changes through time. And of course, the Gulf, like you said, totally correct that there's not really too much data in there. And of course, if we could somehow get all the data from industry, which their databases are probably 10 times larger than Triton, which would be a really incomparable data set to use, would give us a lot better insights into isolated basins such as the Mediterranean, the Indo-Pacific Gateway, and the Gulf of Mexico, all areas which I find really interesting for plankton, because we have this big globally connected environment, which is the marine realm. So how do you have isolation, of genetic isolation to form a new species? So isolated areas such as the Gulf of Mexico and these Mediterranean seas are really important to find out how evolution works in a apparently open marine realm. So yeah, unfortunately, the Gulf is chronically, like the low latitudes, chronically undersampled.
Thank you.
Thank you.
Hey, Adam, thanks for the talk. How do we go about trying to access that database?
Come to my office. I can, if you want, I can make a seminar and talk people through if they want to access it. Show you what you can do with it. Like this, I just sometimes just make random plots of how species distribute. I get bored, so happy to provide code if you want to form any kind of plots. You can put your own data in. Yeah, so happy to give access to anyone.
Nice, but it's not like fully available.
No,
on the
it's,
web.
it's online as well. Yeah, just
Online.
Yeah, if you look for the Triton data set, it'll be in the supplement. So you need a R software. So I can, if you can't access it, I can help.
Thanks.
Any other questions? Okay, it's 11:30, if we could thank Adam again. Thank you all for coming.
Thank you.